I'm gonna work here trying to save that.
Did you like their pranks? I heard you thought it was pretty funny.
Oh, I was laughing all morning.
Yep.
Oh, no pranks. No, I ain't pranking. Did they prank me?
I got a question on yeah, 8. That was a hard one. That was the one I had.
Okay, so I got 8.
Was that one tough?
What else do I have? 13. Okay. Anything else? 8, 13, got your stuff? You gotta have enough to play. And 14? 13. 16. We'll do 16. 8, 13, 16. Let's see, we can be able to see that? Yeah. Anything else? Okay, then I'm gonna go with that. So this was the 5th lesson. And 8 says use a quartet proof.
Mr. Dagan, could you also do 19?
Okay. So that do a quartet proof to show that the diagonals of a rectangle are congruent. Did you work through that?
What?
Number 8, the coordinate proof one.
Number 8, yeah, I did number 8.
Okay, so what did you do?
I graphed that.
Like a rectangle?
Yeah.
And did you use a convenient location?
Yeah, I did.
And where did you place it?
Right on where the X and Y axes intersect.
So you do this?
Yeah.
Okay. So you put it like this. Here's your rectangle. So this point down here is 0, 0. What did you call this point?
I called mine 4, 0.
You called yours 4, 0. What did you call yours?
0A.
0A?
Yeah.
What if we called it A0? Because A is how far across it is, and then 0 is up and down. So then this point up here would be over A and up to B. You called it B. So then that point there has to be 0 left and right, but up B. And then what you're supposed to do is you're supposed to prove these two diagonals to be equal to one another. So then this right here is the hypotenuse with this leg, which is how tall? B, from 0 up to B. And this leg across here is from 0 to A. Therefore, that, call it diagonal number 1 squared. And then if I go this direction, we have a triangle where that hypotenuse has these two associated legs. This leg is B tall also, because A squared then plus B squared is equal to the second diagonal squared by substitution.
The lengths of the diagonal then?
Yeah, doesn't it say use a coordinate proof to show that the diagonals are congruent? And so what we can now say is this is equal to this is equal to that, that's equal to that, therefore that's equal to that. Take the square root of each and then you're done. Okie dokie. Number 13. In the video game below, the mouse runs to east. So 2 east, 3 north. Wait, that's west. Let's go east. East goes to the right. 2. So we can use that. Begins here, goes there. And then 2 more east. And then 3 more north, is that right? Does that twice? Goes 3 north again. And then it goes 2 more east. And then it goes 5 south. And it ends up here. And we need to know how far away it is, I think in a straight line.
What question is this?
This is 13? Yeah, number 13. I didn't draw the nice little grid that they gave here. I didn't do that, I'm just putting it on paper. Because the total distance that it travels east is 2, 4, and 6. So all of this is 6 across. And then it went north 3, 6, but it came back south 5. So that would mean it only has a total of 1 north. So all we need to do is find this distance along here. Can we finish that now? Or 13? Where's 13? We finish that now? Okay. Then we'll go to 16. Find the exact magnitude of a vector from -4, 5 to 7, -11. So essentially what that means is that if you were on the coordinate plane at -4, +5, and then you found this point which is 7 and -11, a vector would be essentially just something like this. Can you see my work? Just tell me if you can't, because I'm not watching myself. So this is much like determining the length of a diagonal or determining the length of a hypotenuse. So we can use the Pythagorean distance formula and just plug these values in. That will give us a vector. Um, 19. What does it mean for 2 segments to bisect each other? Somebody. 2 segments if they bisect. They cross each other, more specifically?
The intersection of the segments is the midpoint of each section.
Yeah, the intersection is going to be the midpoint of each section. So that's going to be a midpoint. And then part B, it says name all of the special types of quadrilaterals whose diagonals bisect each other. So what would be one? Yeah, you could have a square.
Rectangle,
Rectangle? Yep.
kite,
A kite. Now if I did a kite like this, they cross but they do not bisect. So I don't think a kite will fly.
triangle.
That was a joke.
Good one.
You look pretty good, actually.
Yeah,
You set me up though with the kite, thanks. So square, rectangle, what's next? Really? Yeah? Yeah, they're just not the same length diagonals, are they? So a rhombus? Parallelogram. Yeah, is that a center of rotation? Think of it that way. Yeah, so a parallelogram. Is there anything else? Any of the trapezoids?
Isosceles?
Isosceles. I don't know, you know, if you think of an isosceles, make it like this. What, I don't know. Isosceles trapezoid?
I think it works.
You think it works?
Yeah.
I think it works too. And I think that you could probably see that pretty easily on graph paper. I don't have anything good to write with graph paper. But, let's see. And so if we did something like, we're not gonna make a big one. We gotta make a better one. We've got a line of symmetry right here, yes?
Yep.
So if I drew in that diagonal, yeah, ooh, it wasn't a real good drawing. This is supposed to come up a little bit higher. And if it does, I think the intersection ends up being there. But we can look at this as this triangle, which is in the upper right. If I cross this off, the upper right, that triangle is going to be congruent to this triangle. So that is definitely isosceles trapezoid. We would be able to add on to that list. Anything else? Okay. Did you guys bring computers?
Nope.
Do you have yours?
Yes.
You do. Who does not have one? Both of you don't. Okay, we can make it work. It'll be good. It'll work out. We don't have to go running for computers. It's just one little thing to do. So, I'm varying a little bit from how this gets introduced. Whoa, that was kind of spooky. I'm flying off there. That would not be a good joke for Mr. McFeeters. The iPad hit the floor from 5 feet, 6 feet up. So we have a circle. So every radius is the same length. Do you agree?
Yes.
Sweet. Okay. So what I'm going to do is I'm going to draw in a radius. You sure you guys don't want one of those?
Yeah.
So I'm going to draw in a radius conveniently located right here. Oops. That's not very good. Okay. So that radius is going to be the same as any other radius I draw, right?
Yeah.
If this is a perfect circle. Okay, so what I'm going to do is I'm going to take that radius and I'm going to make it a part of a right triangle. So, there we go. And then here's the third side of the triangle. Okay. So, how could you figure out how long the legs of the triangle are? Get a ruler. And where would you measure from and to?
You measure from one side.
Like from here to here?
Yeah.
So since this is on the coordinate plane, what is that point?
Oh, 0.
0. And this point out here is something. Let's say it was 10. Then how long is this? 10. 10 subtract 0, right? So conveniently located the triangle is so that we can just say that if this point out here was 10, that the length is 10. We don't have to mess around with 10 subtract some other number and all of that. So like when you guys were doing the Pythagorean distance formula, your triangles were all over creation, right? Well, this is a very convenient location for this triangle. Because whatever that x value is right there, I just have to subtract 0, and that's the length. How long is this side?
Yeah.
Algebraically, how long is this side? If this side is x, how long is that?
Y.
Y. Because if I come over here, this y value is how high up that is. Conveniently located, that this y value up here, subtract 0, is still equal to that y value. So this side of the triangle is x long, and that side is y long. So how long is the hypotenuse?
X squared plus y squared.
X squared plus y squared, and the square root of that.
Yeah.
Yeah, so if I did x squared plus y squared, that would be equal to the radius squared. Could I put another triangle up there?
Sure.
Sure. How many do you think I could put up there?
8.
4. I only have 4 different colors.
Oh.
I could put up 8, I could put up 20, I could put up 100. And every single one of them is going to have the same radius here, because I have a circle. How long is this side?
X.
It's x. I mean, that's a negative number, right? But it doesn't matter, because when I square it, it becomes positive to give me a length squared. And then this is y. So now I have another point on my circle, which is defined by x squared plus y squared equals r squared. And see, I gotta keep you guys till 2:15, so I'm just gonna do this for a while. What are you laughing at? Everyone thinks it's really funny to laugh at me with Vaseline smeared all over my boards when I walk into school in the morning. Now you get to live through this. Here's another right triangle. How long is this side? It's a negative number, but the length is y, isn't it? It comes from the y, and this comes from the x, and it's x squared plus y squared equals r squared again. What is constant here, what is the same every single time as we go around the circle, is this. All of the x's and y's, there's an infinite number of them. You know, you can just go dot, 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 dot. And when we do that, going way, way back, long, long ago, we said to you guys, okay, well, here's a table of values. Plot your points. Draw a line, because every single point fits together so close that it makes a line. Same thing happens here. You do this for every single possible combination of x and y, as long as when you square them and you add them, it equals the radius squared, you have the equation of a circle. That's it. That's the basic one. So now, do you have your computers? Pop open Desmos. Go to Desmos, but not all of you have a computer. How close is one of yours? Is it like really close?
It's like Miss Matthews.
Grab it. Who else is missing one? Are you sitting next to somebody that has one? That's what you want. If you're going to be sitting next to somebody that has a computer, so just go to desmos.com, bring up graphing, Bring up a graphing calculator and let's do the equation of a circle. So you get x, and then shift 6 raised to the second power, use an arrow to move over, add it to y, raised to the second power, move over, equals, and you can do r, and you'll notice that it says add a slider. That's not a little hamburger that you get at White Castle. Do that. So then you can make your circle however big you want it. I'm just going to leave mine like 1. And then I'm just going to zoom in a little bit. So there's your equation of a circle. So are you guys caught up, sort of? I can't see your screen this time behind you. There. You got it on there? Jacob, you can take care of everything with. You gotta do this. No, head and look down, down. Okay, then we're going to put a twist in it. What's the center of the circle here, first of all? 0, 0. Okay, so that's, the radius of this one is 1. Okay. 1 is kind of convenient for the next 100 years of your math. So what I'm going to do now is I'm just going to click on the colored circle up here so that we don't have to look at it. And I'm going to click down here, we're going to enter a new equation. And here's the equation I'd like you to enter. I'd like you just to do this, and then we're going to toy around with it. It's going to be parentheses x minus, and then use the letter h, parentheses raised to the second power. And then we're going to do plus y subtract k, parentheses raised to the second power. So what we're doing is we're adding a subtraction of h and a subtraction of k to the x and the y's. And we're still going to say that that's equal to r squared. And then you want to add a slider for everything. And I think you're probably going to end up with something like mine. Might be a different color. You can't?
Oh.
Yeah, it's a, yeah, we're good. So you might get a different color circle, but you should get a circle. Did yours end up over there in quadrant number 1? And you can turn off your first one by just clicking next to the equation, the little colored circle that's got the squiggly line in it. Okay, so that circle doesn't end up over 0, 0, does it? But if you look before you start changing h and k, what are your h and k values? Oopsies. So what are the h and k values? 1 and 1. What's the center of that circle? 1, 1. So what you can do now is you can change your h value and make it smaller, like make it 0. And you can make k to 0. And look, now we're back where we started, aren't we? And toy around with it. When you change h, when you make it bigger, which way does your circle move? It moves to the left or the right as you change your h value. But it's important to know if h becomes greater, the direction that the circle moves. So when you increase h, which way does the circle move? Moves it to the right. And when you increase k, which direction does the circle move? It moves up. So why don't you change your h value to like 2 and your k value to -3 and find your circle if it left the screen. So if you change your h and your k value to 2 and -3, where's the center of the circle end up? 2, -3. So in this form of the equation, where we throw h and k into the mix, h and k tell us where the center of our circle is. Yeah. These are all cattywampus, huh? Why is it wrong?
I don't know.
Okay, just put a -3. And now, you go to one further. And now if you look at 2 -3, that one right there. So now what I'm going to do is I'm going to change the equation of the circle. We're going to write it like this. X minus h quantity x minus h squared plus quantity y minus k squared is equal to r squared. And then underneath that I'm going to write as an ordered pair h comma k, and that is going to be the center of the circle. R is the radius of the circle. That's the formula for a circle.
So what is the first one for? Just the triangle?
This one right here, no, this is still a circle, but that's a circle with the center of the circle at the origin. So if h and k are both 0, then the center of the circle is 0, 0, the origin. So I just started with that one to make it a little less complicated. Imagine, what if I put this up right away? That's a little scary looking, right? It's still kind of scary looking. But that right there, that's the formal, complete equation of a circle. There it is. That's the equation of the circle. And then plug in somewhere else now. So if we looked at this example here, I'm going to blow through these pretty quickly because they're in the book. But if we look at this example here, they have our circle drawn in. They drew in a radius of this. This is all right in your book if you need to look at a better picture. And they're asking for us to write an equation of a circle. And if we use this form up here, where h and k are the center, all we have to do is look at the center, which is, what is that point?
Or -2.
4, -2. And that's going to be our h and our k value. And all we do is substitute that in. And then we can say that the equation of this is going to be h is 4. And then y is -2. So if we're subtracting -2, we should write that as the addition of 2. And then instead of r squared, what is the radius if you count it up? That's 6. And 6 squared will be 36. So if you put that into Desmos or into your graphing well, you know, not your graphing calculator. These are hard to put into the graphing calculator because they have to be in the form y equals. And I'm not going to go there in this class. We'll do that next year. But you have to put it into a graphing calculator in 2 parts. It's not easy. Once you see it, it's okay, but we're not going to go there today.
Did you get 36?
I took 36 because the radius in this case is 6, and this would be r squared.
Radius is
The
6.
radius, so going from 4 out to 12 is a distance of,
Oh, okay.
oh, no, no, this is 12 right here, from 4 to 10. 4, 6, 8, 10. So that's a radius of 6. 6 squared is 36. Okay, so here's another problem that they throw at us. They give us a circle. It's the same circle again. So it has that same equation. And that equation is going to be x is subtract 4 squared plus the quantity y plus 2 squared is equal to 36. And they say when we have this line where x is equal to 7, so we're asking ourselves, if the x value is 7, what y value are we going to get? At the same time, if we follow down the x equals 7 line and we hit this point on the circle, we're going to come over here and we're going to get a second y value. So what they're asking us to do is to take this circle and solve the equation for where x is equal to 7. What is this point? You know, they're asking you, what's the ordered pair of that point? We know that the x value is 7, but we now need to find out y. And then down below here, it's also x is equal to 7, and again, the y value is what we're looking for. So what we have to do is we have to go into the equation for this circle, substitute the x value 7 into the equation, and solve for y. So there's a lot of order of operations we've got to keep track of here because we've got y buried inside of this set of parentheses and it's being squared. So you got to kind of pay attention to that. So here's the trick with this. If we put 7 in for x, rewrite the whole equation. Seven subtract 4 is
3.
3 squared is
9.
next step. Subtract 9. 36 subtract 9 is 27. So now I have the quantity y plus 2 squared. You don't want to remove the parentheses. Because, I mean, you can, but when you get to a point like this where you have just one quantity in parentheses being squared, the best move is to take the square root. So now this becomes y plus 2 is equal to the square root of 27. But there's a little trick here. You realize we could have something in here that gets squared, and it could be that number 27. But there's 2 things that you could square to get a 27. You could take a positive times a positive and get a 27, or you could take a negative number times a negative number and get a 27. So that means whatever is in here, this y plus 2, can show up as either a positive value or a negative value. So this square root of 27 can be a positive, or it can show up being a negative. So we have to account for that. It's kind of like doing absolute values. We would find that there's 2 possible combinations because inside the bars it could be a negative number or a positive number to give you your answer. So this is an important step right here. So in essence what this does is it makes it so I have 2 things to solve. Y plus 2 is going to be equal to the square root of 27, and y plus 2 is gonna be equal to the negative square root of 27. So we'll solve the top one first. We subtract 2 from both sides, and then you get y is equal to negative 2 plus the square root of 27. And on the bottom, if I subtract 2 from both sides, that will be a negative 2 subtract the square root of 27. Those are your answers. Those are the places where x is 7 and y is either one of these two numbers. So up here is the positive number, and there's the negative number. So it gets a little complicated. It helps to keep everything nice and orderly, left to right, up and down. So what is the square root of 27 approximately?
5.1.
5.1, okay. So I'm going to come over here and I'm going to say that this first solution is negative 2 plus, let's say, 5.1. So that's about 3.1. And then the other solution is a negative 2 minus 5.1. So that's about a negative 7.1. So this is about a negative 7.1 and about a positive 3.1. And that makes sense. That's what it looks like on the graph. But these are the exact values. Keep that in mind. No fooling. That's how it works.
Wait.
I'm not like we're joking around. You want me to put it up?
Yeah.
Sure. Is that good?
Yeah.
It's pretty cool shot. So take a look at the third example. It's called a guided example. We've got some blanks for us to fill in. See if you can go on that one. Find the H, find the K, find the R value, the center, and the radius. I don't have the page number.
What is it?
Sorry.
It's 11.5.
684.
5?
4.
4? Yeah. Top is 684. It looks something like this one right here, up top side. So they give us the form of the equation, and then they say this is the equation, here it is, and again down here. So from that form, can you dig out of this equation an H value? And then a K value. Watch your negatives. Unless you said something ahead of that number.
I might want to make
equation is y, h minus k and y minus k. Okay.
Maybe what he did, we'll have to make sure it's something we can access to see later. The Desmos.
Or Desmos.
Yeah. Yeah. So you're kind of familiar with? Yeah.
X squared. X squared. Plus y.
Oh.
Yeah. Okay, so so you're supposed to find what is h and what is k. You did that, and then why is the center different? Oops. So in order to take this and have that, what does h have to be? What number would you put in for h? So that when you take x minus that number and have it squared, it equals just x squared. If you put the number 1 in there, you're not going to end up with x squared, right? If you put the number 2 or number 3 or number 4, it's not going to work, is it? So what does the h have to be so that you have only x squared when you're done? 0. Yes. Okay, h. And then h is 0. And then we'll find h is 0. This is 1 minus 5 is the same as 1. Well, don't change that. That's the equation. Only what it looks like. I would say that. What do you have so far?
But it says like,
That's all incorrect, that's all incorrect in a lot.
Yeah.
We're not solving these yet.
Yeah.
Solving them is way out there. So where's your h value? Okay, so the form of the equation is x minus h quantity squared, and you compare that to this. So if you compare that, well, this is not, this is way invalid. I need pencils too. Can I give you one yesterday?
Yeah.
Can't give you one every single day, but we get close.
Yeah.
Okay. So if you have x minus h is equal to x squared, our question, first question is, what value of h has to be put in here when you say x minus that number, you'll end up with only x squared. Yeah, it's gonna be 0, so h is gonna be 0. And then you look over at the y minus k and compare it to what the equation says. And that says 5, and that's subtraction. So if you rewrite this as subtraction, then you'll know what your number is. Don't change the equation, but say y plus 5 is equal to y minus. So instead of adding 5, if you subtract, what will give you the same answer? Not okay, you're not certain. Yeah. Okay, so another way for writing subtraction is the addition of a negative. So for example, if you had a plus 5 plus a negative 5, that would be the same as a minus the 5. So the addition of a negative is subtraction. If I was to say that I had something like c subtract negative 5, what is that the same as? If I rewrite this as addition, what would this be? C subtract a negative 5 is the same as c plus 5. So we can take addition and rewrite it as the subtraction of a negative. That's what you're looking at in that y and k value. We okay over here? I'm digging it out.
Someone already told you that.
Yes.
Okay. So let me see. A little bit further on the line is this one here. Have you guys looked ahead at the fourth example? I am going to drill through all of them. They give you a point, -8, 2, and they ask, is it on the inside or the outside of the circle? So you could graph everything, right? That'd be one way to do it, but we're beyond that. We'd like to try to do it algebraically, using the ideas behind equation of a circle, including stuff like the radius and the center of the circle, where these things are all located. So this is kind of a challenging problem. And we're using the same equation as what you guys had, which is going to be, I'm going to write it a little bit bigger, x squared plus y plus 5 squared is equal to 100. And we're taking -8, 2, and we're trying to find out, is that on the inside, the outside, or is it on the circle? So, if we put -8 in for x, and we put 2 in for y, and we do all of the work, if it's equal to 100, that means it lands right on the circle. And that would be really easy. So if we do that, we took quantity -8 squared plus the quantity 2 plus 5 squared. Does that add up to 100?
No.
No. 2 plus 5 equals, squared is, -8 squared is, it's not 100, is it? It's 113. So, if this is our circle, and we know that the triangle with the sides of a length of 8 and a length of 2 are placed on here, and when we square these two numbers, we end up with something that's too big for the radius. In other words, it has a larger radius. So this calculation here is bigger than 100. That 100 comes from the radius squared. So in other words, in this case here, that radius is 10. So we go to everything that we have here, we say, well, that's equal to 10 for the equation. But now we have some triangle, which is negative 8, 2. And when we take negative 8 times negative 8, so we take the side of some triangle squared plus the side of another, or the other side squared, and we add them together, we get something that's going to be bigger than that number squared. So that puts that point of the triangle, of our imaginary triangle that is drawn out to negative 8, 2, it puts it outside of the circle. So when this quantity here is greater than the radius squared, it had to come from a bigger triangle than what fits on the circle. So the point is outside. If this number here was smaller, then it would be fitting on the inside of the circle. Imagine, if you would, the point 1, 1. It'd be like over and up. It'd be 1 squared plus 1 squared, and that would give you a radius of the square root of 2. Be really small little triangle. That radius of 2 is nowhere near a radius of 10. So having a point that's really close to the origin isn't going to fit inside of that circle. Do you agree, Mrs. Dagan? Do you really? Does it work?
I'm hiding behind my stuffed animal.
I have lots of stuff in. I don't want them though. Send them away. Here's the last one. So here they have the line y equals 11, so there's 2 points of intersection on the circle. And what we're doing is we're supposed to find the x values. So it's just like the second example where we had to find 2 different locations. Or no, it's the first example, pardon me, where we had to find 2 different locations for, well, this isn't it. It was the second example. Too much paper. Now it's lost.
Turn that one sideways.
Yeah. Here we go. This one right here, where we had to find these 2 different values of y when x was given to be 7. The last example is exactly the same idea. We're getting 2 different values of x when y is said to be equal to the same number. So, now you guys want to go home and do like 45 problems? What would be wrong with that? How many problems do you want to do tonight, Arik?
8 was pretty good.
8 of them.
Yeah, I like that.
So number 3, number 5. Number 7. Number 9. You don't want 8. 11. 3, 5, 7, 9, 11. This isn't hard. You remember this. And then number 14. So that's 1, 2, 3, 4, 5. That's 6 problems.
What page is this?
Oh, it's 685? Yep, 685.
I don't know if I can do it.
You sure? Okay, that's only 6 problems. You said you wanted 8.
Six sound good.
It sounds great.
Yeah. Ours was 6. Well, yeah, I changed my mind. I actually like 6 more.
6. Okay, we'll go halfway between. 16. 3, 5, 7, 9, 11, 14, 16.